In the last video, we saw the true meaning of the two postulates of special relativity. Now let us see how Einstein used them to build the theory. The early 1900s were an era of railway expansion across Europe. Clock syncing between stations became very important, and applications to patent clock syncing methods were flooding patent offices. A clerk in one such office was seeing many such applications, and he was simultaneously pondering over the constancy of light speed. He realized that an unchanging light speed will pose challenges to clock syncing between two moving observers. He started conducting thought experiments involving a person on a moving train and another standing on the track. Albert is standing at the exact midpoint of this train carriage. It is the midpoint because a stick from this point to the front end exactly fits from this point to the rear end. Two clocks start at the front and rear end. Each flash and release a photon. The two photons reach Albert at the same moment. Now Albert knows he is in the middle, so he concludes that both photons must have left at the same instant, and so both clocks are synchronized. The flashes are simultaneous for Albert, which means that the clocks are synchronized for Albert. But what about Ben, who's standing on the tracks, observing the train moving at a speed v? He also sees the two photons reaching Albert simultaneously, because the meeting of the two photons is an event that occurs at the same place and time. Everyone in the universe will observe it as one event. So what does Ben infer from this? Let's see what classical mechanics has to say about this event. Suppose these were two balls instead of two photons, reaching Albert at the same time, thrown by two machines at equal velocities. Albert would deduce that they were thrown simultaneously, and Ben, on the other hand, would see the rear ball traveling at a velocity u plus v, covering a distance ut plus vt, and the front ball at u minus v covering ut minus vt. He would also infer that both balls covered equal distances and the throwings were simultaneous. But here, Ben sees the photons reaching at the same time, traveling at the same speed but covering unequal distances. He has to infer that the rear photon left earlier and that the rear clock is ahead of the front. The rear clock started before the front clock. It showed 00 before the front clock. This is the relativity of simultaneity. If two clocks are at a distance from each other, a time difference arises for an observer moving relative to them. The rear clock appears to be ahead. If there is a third friend Chris on a parallel track moving in the same direction as Albert at double the speed, then for him this becomes the rear clock and this clock is ahead. For Einstein, this loss of simultaneity was the fundamental reason for all the non-classical effects of relativity. Can we see it intuitively without math? Yes. It is kind of obvious that the time differences between these clocks would be proportional to the relative speed and the distance between these clocks, right? It may be proportional to the square or square root, but it is proportional. The faster this carriage moves and the longer it is, the more this clock will be ahead. If this clock crosses him at 00, this one, according to him, should be showing 01 at the same instant. Now when this clock is crossing him, he looks at his watch, notes it is 03. So what does he conclude? That this clock reached him in just 2 seconds according to itself, when 3 seconds have passed in Ben's clock. If all these carriages have a clock at the rear end, all these clocks are taking 2 seconds when Ben's clock takes 3 seconds. The time on this train is running slower. I can almost hear you explaining that this approach is unnecessarily complicated. The light clock with the bouncing photon is a neater way to explain time dilation. And traditionally, we learn time dilation with that bouncing photon and loss of simultaneity with this train. But one should lead to another. In fact, both are the same things. Like a speed of 10 km per hour is same as a pace of 6 minutes per kilometer. And to drive this point home, let us see how it leads to length contraction. So Ben calls Albert and informs him that his clocks are not synchronized. Albert vehemently denies it. No, they are perfectly in sync. Oh really? Then why are the carriages crossing me in 2 seconds instead of 3? Aha! They must be shorter. Instead of 30 meters, they are 20 meters long. So, either the clocks are not in sync, or time is slower, or length is contracted. It's the same thing. We can't say which one is more fundamental. In fact, we can't even say whether the constancy of C causes these effects or one of these effects leads to a constant C. A constant C was observed before we could observe time dilation or length contraction, which made Einstein use that as a postulate. But if you look at people before him, like Lorentz, for them length contraction gave rise to a constant C. Oh yes, we can also add the relativistic velocity addition to these three. Once you have accepted the second postulate, everything else just follows from it. Then why does relativity still feel so unintuitive? Because deriving everything from the second postulate has to be mathematical. They come via equations. But is there a more direct way? Yes, we will see that approach in the next video, and understanding things will become so easy. Let me give you a hint. What is the solution to this system of equations? C plus x is equal to C minus x is equal to C plus y is equal to C minus y is equal to C plus z is equal to C minus z is equal to C. Comment with the answer. Stay tuned for the next video.